All right, let's get started. We got a busy day ahead of us, and good news, you'll get out early because it's the lab day. But let's get started. Good afternoon, everybody. Welcome to a sunny, wonderful afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. And there are a number of things I want to do, but first, I want to share something with you. I got a while ago, but my best friend, who I've known over 50 years, we were friends, met each other in sophomore, junior year of high school. We've been friends ever since. And his wife is a very nice woman. I'm friends with her, which is not always the case. You're friends with one person of a couple, doesn't mean you're friends with both. But anyways, she teaches in Fort Wayne, K through 3 or first, second, third grade. And she sent me a nice cartoon a while back, and I thought I'd share it with you. Does everybody see the cartoon on the screen? Hold on. Yep, you see it? I thought you'd enjoy it. And no, I don't smoke. I used to years ago, but a couple of times I wonder, where are my students? And no, I wasn't looking at the microwave. All right. Now, I sent out early this morning, and I didn't open up, so I better open it up now. Get to D2L. All right, everybody should see on your screen now, test 1, information. This, about 8 o'clock this morning, I sent out, first I posted an announcement here, and you were also emailed with this. And let's go through it. On Thursday, a week from tomorrow, I will be giving test number 1 online. How do I do that? You'll be downloading a password-protected PDF file from the assignment area of D2L, just like you've been doing your labs, and that will be available starting Wednesday afternoon. Since it's password protected, you can't open it up yet. On the next Thursday or next day, the 24th, after class, I will send out an email with the password for that PDF file. That's number 1. You will have until Friday, the next day, the 25th, 10 a.m., to finish test number 1, upload your test number 1 answer as a single, and that's important, single PDF file to the assignment area D2L. Should take you about 40 minutes to do the test, some people less. Normally I give in a face-to-face, you got about 50, 55 minutes, take up to an hour or so to do the test. The test has 10 pages, which has 14 problems. Some of the problems are multiple part, like A, B, and C, but there are no multiple choice. In Chem 170, I have never, ever given a multiple choice question on a test or final of mine. Now, it will cover, I don't know the exact chapters, but hydrocarbons, alkanes, cycloalkanes, alkenes, alkynes, and aromatic compounds. This test, as with all my tests in the final, is not open note and open internet and open get help from a friend. That's called cheating. Please don't. I have things in my test that will indicate when I can catch people, and I have since the pandemic started. Now, here's the point breakdown for test number 1. General knowledge will be 13 points. Nomenclature, remember there are 2 types of nomenclature questions. One is, here's the structure, give the IUPAC name. The other is here's the name, draw the structure. And then there'll be 47 points with reactions. All but one problem will be give the product or products for the following reaction. One problem, and only one, because the Supreme Court still has outlawed cruel and usual punishment to students, so I don't do more than one on the first test. There'll be a synthesis, what I call a synthesis, and that's give the starting materials for the following reaction, or the reaction that makes this product. And if you notice, it adds up to 105. Why? Because there's 5, yes, 5 bonus points. Now, which are the 5 bonus points? You pick them. I don't have one problem say, this is the bonus problem. No, I just had the whole test add up to 105 points. So there's an extra 5 points you could earn. And that's how I do my test. And it makes sense and it helps students. And also, I can sometimes put interesting problems on there because I'm giving you 5 bonus points. Now, please read the attached files, which also went out in your email, how to upload tests. It's similar, the same thing as you were doing for the lab. I will do a review of the material on test 1 in next week's Tuesday Zoom meeting. We will, even though at the end of the meeting, I'll be sending out the password, next Thursday, we'll have our regular Zoom lecture meeting. And with that, I have down here the attachments, which you've seen before, and it was also sent out to the email to you. Now, a couple things about my test. One is every problem I put on a test, I've talked about the concept behind that problem at least twice, a lot more than twice, but minimum twice. The only thing I don't cover on a test that's on a test is, what's your name? Which is a question. You got to put down your name. Other than that, everything's been covered in the lecture at least twice. As a student, I didn't like, we never covered that stuff. How's that question on the test? I had one teacher in physics, and we actually got him fired, would find footnotes in the chapter that were hidden, and he'd ask questions on that, and it wasn't even the most important stuff of that chapter. Awful. But anyways, I don't do that because I follow my golden rule of teaching. I don't do to my students what I didn't like done to me. Now, what I will tell you is, unlike the labs, I've found a way to send back to you after I've graded it how many points you got for each question. I'll send you each individual email, and like question 4, say it's A, B, and C, and D, you'll see 4 or 8, 3 points, 2 or 0. If it's a 3-point question, what you got. And I'll do that for the whole test, and that will get sent to you. Now, as you've heard me say multiple times, there's no such thing as a dumb question in my world. And a very good question is, why did I lose points on that? I don't answer those during the lecture. I do that after lecture privately or during my office hour. If I'd been handing it back to you, the actual paper, you'd see on there why I marked it wrong, but I can't do that the way I have my test set up, which worked quite well. We've been doing it now. This is the, what, last spring, summer. This is the 4th semester I've been on Zoom. The first one, we sort of halfway through, you ain't coming to school anymore. And we have to scramble. How do we do this? That was not a fun time, but things turned out well. All right, one other thing, listen carefully. On reactions, when I ask you give the reaction product or products for a reaction, the answer, no reaction, will never, ever be correct on my test. I'll say that again. When I ask on a test, give the reaction product or products for the following reaction, the answer, no reaction, will never, ever be correct on a test. I hated that when I was an undergrad. Here's a test, you ask me, give the products, and you want the answer, no reaction? Well, why'd you ask the question? It doesn't make sense in my mind, so I never will do that. And with that, I'll ask, are there any questions about test number 1? And if you're uncomfortable asking questions, always feel free to see me after class or come to my office hours. And you can always email me at kwhite@elgin.edu. Remember, I might have mentioned this, but maybe I didn't in here. I check my email twice a day religiously, every day, Monday through Sunday. However, my day and your day are different. Since I've been about 5, I'm usually up and running, starting doing stuff by 5 a.m. I go to bed about 11:30. My parents, when I was young, used to get in bed. No, I don't want. I'll get up too early, get in bed. And I did, and I'd be reading with a flashlight under the bed covers. And are you sleeping at? No. But anyways, so first time I usually check my email is somewhere around 5:30, 6 a.m. And then later in the afternoon or evening, I'll check it for a second time, unless unfortunately something unusual happens. But I guarantee I will check it at least once, but most likely I always check it twice. Any questions before I continue? All right. I promised today I'd go through the aromatic problem set, so I better keep my promise, because Dr. White does not break his word unless something unusual comes up. Not wrong thing. Right thing. Quick thing, thumbs up, people. You see an aromatic problem set on your screen? Do you see it? Okay, thank you. All right, let's go through it. Give the IUPAC name for the following molecule. Well, methyl group on a benzene ring. Again, look for what's different. 3 double bonds conjugated. Conjugated means alternating, single, double, single, double, single, double. I've never seen where it's unconjugated like that in a ring, but anyways, that's toluene. Now, if you notice here, B, we have an NO2 group, that's the nitro. Remember, you should know nitro, chloro, fluoro, bromo, and iodo. And disubstitute, even though it's toluene, the methyl group is considered substituent in the nomenclature. And notice it's 1,2 disubstituted, and we use ortho. And remember, ortho is 1,2 disubstituted, meta is 1,3, and para is 1,4. This is only for aromatic compounds. Please do not use it for cyclohexane. I'll mark it wrong. And I have on tests, which is why I'm telling you, don't use it for that. And if we look here, it's 1,2 disubstitute, NO2 nitro, so it's orthonitrotoluene. And if we look at C, benzene ring, ethyl group, isopropyl, and it's para-ethyl isopropyl. Why para? Because it's 1,4 disubstituted. Now, since I'm not holding you to the alphabetical rule, if you put down para-isopropyl ethyl, I would give you full credit. And if you have more than one group, you use numbers. Notice here in E, I have not 1, not 2, but 3 bromo groups. Br, bromine, bromine is called a bromo group. And when you have 2, it's di, 3, tri. Now, where are they? I'll call this one 1. This is on carbon 3. This is on carbon 5. When you have di, you need 2 numbers, tri, 3 numbers. So it's 1,3,5 tribromobenzene. Now, on test number 1, you saw I had, what was that? I think 45 nomenclature points, somewhere around that ballpark figure. And there are 2 questions. One, here's the structure, give the IUPAC name. And the other is draw the condensed structure for the following. Now, condensed means you don't shove carbon, hydrogen, single bonds. You write CH3 instead of C with 3 hydrogens showing. And for benzene, here I have the structures. Now, let me remind you, when you draw a benzene ring, you can draw it like this. Here's another resonance form, which is equivalent. Or you can draw it with this circle. Dr. White likes these. This is acceptable, but I don't think this is cool looking. Now, if you do this on a test where you're drawing a benzene ring, that's wrong, because that's cyclohexane, which is different from benzene as your nose is from your ear, or night and day. So make sure you put in the bonds or the circle for the delocalized structure, that's what that's called officially, when you do a benzene ring. Now, how do you decode the name? All organic compounds, you start from the right, move left. Benzene, well, here's my benzene ring. I have on there a chloro and ethyl, and I actually got that wrong. It should be chloroethyl, not ethyl chloro. See, Dr. White makes a mistake. And it's para. Para means 1,4. So I have the chlorine on top, the ethyl group on the bottom. You could have switched them, and that's how you do it. And if we look at, excuse me, let me move this out of the way. If we look at C, metabromo, that's toluene. Excuse me, I'm going to drink some water. I got a frog in my throat, not really, but that's better. Test, ketone, that's working fine now. All right, start from the right, move left, toluene. Now I did it my way, but you would probably put the methyl group on the top, and bromine, and it's meta, so it's 1,3. And let me write the way you probably would have done. That's not what I want. That's what I want. And the way most of you would have done metabromotoluene, I put my bonds, my methyl group. Meta is 1, 2, 3, and I put my bromine. You could have gone the other way, which would be perfectly correct. 1, 2, 3. And all I've done is rotate A to B by 180 degrees. That's all. Flip it. And either one of those would have been correct on test also. Now, when you have more than one, I forgot to put the di, bad Dr. White, 1-ethyl 2,3 di and propyl benzene, start from the right, move left, benzene ring. I have on carbons 2 and 3 and propyl on carbon 1 ethyl. Here's my ethyl and propyl, 3 carbons, the end carbon of those 3 is bonded to the chain or ring. And here I have 2,4 dichlorotoluene. Start from the right, go this way, toluene. Benzene ring with a methyl group on it. Chloro, Cl, di, 2, and some carbons 2 and 4. The methyl group is 1. 2 and 4. All right. Now, when it comes to reactions, well, oh, guess what I didn't do? I didn't write down the general reaction here. We have benzene plus chlorine and ferric trichloride. You get this molecule. Let me do this. And the general reaction is a benzene ring. Chlorine gas is a halogen gas. And you have this catalyst, ferric trihalide, in this case, ferric trichloride. And X here is chlorine or bromine. The others might work, but I think it's because it's expensive. It's never done. And you replace one of the hydrogens on the benzene ring. Now remember to put the bonds like I'm doing. So I had a student didn't do it and lost 12 points out of 105 because she forgot to put in the bonds or circle in her answers for aromatic reactions. So I have my benzene ring and my X in this case is chlorine. And the only other one I can give you is with X being bromine, which I do. And there it is. Now, the next reaction, we look here. What do we have? Benzene. Remember, above and below the arrow like this means they're reacting with that. I have, ooh, what's different? Carbon, oh, a halogen on a carbon, RX, alkyl halide, and aluminum trihalide. And this is Friedel-Crafts alkylation. You put an R group on the benzene ring. The carbon with the halogen is the carbon this R group is going to be bonded to. Hold on one sec. Two more rings, my answer will pick it up. I'm sorry. One more. Stop. Thank you. All right. The carbon with the halogen, well, in this case, only one, and RX will be bonded to the benzene ring here. And this is probably an expensive way of making toluene, but it gets you started. Let's move to the next one, page. And here, let's look at E. I have a benzene ring. Ooh, this is different. What's different? Ooh, halogen on a carbon. RX, the R is the cyclopentane ring, and the catalyst aluminum trichloride, and this is what you get. You know, I'm going to share the fun. What would be the organic product or products for the following reaction? 3 points each. Your turn to have some fun. Am I a nice person or what? The answer is or what? No, I'm kidding. If you're done, give me a thumbs up. If you're not done, don't give me a thumbs up. Or I can go high tech. All right, I think just about everybody's done. So I better get to work. Now, how do you do this? You look for what's different. Benzene ring, that's different. Good news on my tests, like the problem sets where I have my software. I use ChemDraw, the best out there, to do this. All right, what's different here? You look for what's not a carbon-carbon single bond or what's not carbon or hydrogen. Oh, look, a halogen chlorine on that, and that's Rx, where this is my R group. And I have aluminum trichloride, which I can abbreviate this. And remember, X can be chlorine or bromine. And what happens is you put an R group, you do something very special, very rare, you make a carbon-carbon single bond. Now, which carbon in the R group has the halogen? This one. Therefore, that's the one that will be bonded to my benzene ring. And remember, there's 4 bonds to carbon. Now, if you look at that answer, it's wrong. Why? Because that's a cyclohexane ring. Don't forget, and the student I told you lost it would leave this. She forgot, and you don't know who I'm talking about, so I can say she. She forgot in Chem 170. In the past, the majority of the students have been she, so you don't know who I'm talking about, to put the double bonds or circle in there. And you get N-propyl benzene. And that's how you do it. Now, there's only one reaction I can give you for F, and here it is. You take benzene ring, react it with sulfur trioxide and sulfuric acid, H2SO4. You put on a sulfonic acid group. Don't forget the H. And because I'm not doing directors, this is the only problem I can ask with this reaction. And the last one, same thing. Since I'm not doing directors on the test or teaching it in the lecture, I have a benzene ring, HNO3, nitric acid, H2SO4, sulfuric acid. That forms the nitronium ion, which I'll teach you in lab today. But you put a nitro group, and that's NO2, not NO3. You put NO3, I'll mark it wrong because you proved you didn't know what you're doing. Make sure you pay attention to what you're writing down. It's important. And with that, we've done the problem set. Are there any questions about aromatic compounds? Speaking about aromatic compounds, does anybody happen to smell cinnamon or vanilla extract? Those are all aromatic compounds. Now, I never really showed you the structure of cinnamon. Let me log out of this. All right, this won't be on a test or anything, but if you see on your screen right now, to the right, you see that structure? Oh, it's a benzene ring with a double bond, and we'll learn later on, this is called an aldehyde. And this is the molecule in cinnamon that gives it its taste and flavor. If you notice a benzene ring, it's aromatic. Oh, let's do one more because I didn't do it for you. All right, does everybody see on their screen the vanillin in the upper right? This is the structure of the main molecule, vanilla extract, that gives it its taste and flavor. Well, I guess taste and flavor are the same thing, taste and smell. And notice the benzene ring. There's a lot of other stuff I'll teach you that's on there. And that's the molecule Mother Nature made to give that fantastic taste and smell. I should warn you, Dr. White's a vanilla extract freak. I love vanilla extract. I like cinnamon too, but vanilla extract, whoa. I think I've told you I get it from the Spice House online, even though it's in Evanston, the great place to get your spices. All right. Any other questions about aromatic compounds? Once, twice, three times. So let's move back to alcohols. Now, yesterday we started alcohols. And what is an alcohol? Remember, an alcohol is any molecule that has carbon with a hydroxyl group. Hydroxyl group is on carbon. OH gives you an alcohol. And we learned alcohol nomenclature. Find the longest chain or on the ring that has the hydroxyl group, that carbon, name that whole chain or ring as an alkane or cycloalkane. Drop the E, add OL, acyclic, not in a ring. You need a number. And then cyclic, no number when it's the only functional group in a ring, which in this class that will be the case, because that's always going to be number one. That everybody knows that. So I put a number down when everybody knows it, and you do too. So let's do a little practice from what we did yesterday. And I will ask you, give the IUPAC name for the following molecule. Your turn. And when you're done, give me a thumbs up. I'm done. If you're done early, please be patient. I try and give everybody time to finish. Oh, I just thought it's Wednesday, my favorite program of the almost the week. One of them is on tonight, and that's Forged in Fire. If you've ever seen that, it's interesting about knife smithing. One of my hobbies is unusual weapons, and I think partly also my father got me into it. I have a nice collection of pocket knives and other knives. I'm not into guns, never have been. They're too dangerous to have around the house. But anyways, I better get to work because people are giving me that look, get to work. All right, look at a molecule, look for what's different. Hydroxyl group on a carbon, alcohol. And what's the longest chain? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, or 6, 7. So the longest chain is 7. And I have my hydroxyl group on carbon 2. 7 carbons, heptane. Drop the E. Remember, alcohol, find the longest chain with the hydroxyl group, name it as an alkane or cycloalkane. Drop the E and replace it with OL. And so I will, heptanol. And what number is the hydroxyl group on? Carbon 2. That's 2-heptanol. And as soon as I say that, that's all spoken for. What do we have left? Oh, it's your old friend, the methyl group. But we've got 2 of them. And so methyl, how do we say 2? Di. So it's dimethyl. And when you see 2 di, you need 2 numbers. Was tri, you need 3. And it's on carbon 5 and 6. So this would be 5, 6 dimethyl 2-heptanol. Now, there's another skill you should have. Here's the name, draw the structure. And why don't you draw the structure for 3-T-butyl? I'm going to be a lazy organic chemist, which I am. And instead of saying tert-butyl, I'm going to be using T-butyl like all organic chemists do. 3-tert-butyl cyclohexanol. Draw the structure, please. And for those who already gave the thumbs up, thank you. Well, I think everybody's just about done. How do you decode this? All organic compounds, you start from the right and go left. OL ending, alcohol, hydroxyl group on a carbon. Ooh, cyclohexane, if that were an E, I know what that is. So I have a hydroxyl group on a cyclohexane ring. That's carbon 1, carbon 3, 1, 2, 3. You go clockwise or counterclockwise. They're both the same. This is my favorite, one of my favorite alkyl groups, a T-butyl group. And that's a little quick review of nomenclature of alcohols. Now we're not done. Now, when you have, and everybody see nomenclature of phenols on their screen? Thank you. I assume you do. All right. When you have a hydroxyl group on a benzene ring, that's not called benzol. It's called phenol. Now, some of you have heard pronounced phenol, which is incorrect. I worked at a company and we bought, I don't know how many million pounds of phenol a year. And I had a running argument with the chemist there at the plant in Kentucky and the research center. I called it phenol. They called it phenol. If you're in England, it's called phenol too. But anyways, I'm going to call it phenol. Good news, I'm not giving pronunciation quizzes or tests. But phenol is a hydroxyl group on benzene. And similar to toluene, if you had something on there, you'd use orthomet and para. Like if you had an ethyl group in the 2 position, that'd be 2-ethyl phenol. But phenol is named as the IUPAC people said, we'll use the common name because we're not going to change organic chemists who've been calling this phenol for eons. Now, how many of you have ever put a certain product on your lips called Carmex and you feel that tingling when you put it on your lips? It has phenol in it, and phenol has antimicrobial, antibacterial properties. And it's also acidic, and that's why you're feeling that tingling. I used to have one here for show and tell, but I guess I put it back in my bathroom. Since the pandemic, I don't go out that often, and which is all right, just keep me healthy. But that's phenol. Now, we're going to be getting into a part, the next couple chapters, like the next 5 or 6, where the new functional groups, in this case, the functional group I'm teaching, alcohols, have been around for a long time. If you think about it, the Egyptians and the Romans were centuries and centuries, millennia ago, were making alcoholic beverages such as beer and wine. I don't know if they had hard spirits. I'm going to bet they might, but I don't know. I'm not an expert in the history of alcohol. But certain alcohols have common names. And these key alcohols are more likely that common names are used instead of IUPAC. How do you derive a common name? The common name is derived by naming the chain the hydroxyl group is on or attached to as an alkyl group, and then adding the word alcohol. Now, if I look at the clock, I think I can get it in before our break. If not, I may go a minute afterward. You'll still get your 5 minutes. I don't cheat students out of their break. And let's take a look at it. It says, look at the board. I'm not the board. Here's the board. All right, let's get to work. And this is something you should know. Remember, the stuff I'm doing on alcohol is test 2, not test 1. All right, the first one. This is 2 carbons, ethane, alcohol, drop the add OL, ethanol. Now, if I look at this group, what do we call 2 carbons? We call that an ethyl group. And it's an alcohol, So the common name would be ethyl alcohol. And if you look on wine bottles, they usually have ethyl alcohol instead of ethanol. Now, let's look at this one. It's got 1, 2, 3 carbons. That's propane. Drop the E, propanol, and the hydroxyl group is on carbon 2-propanol. However, nobody calls it that. We look at this group that I'm circling in red. What is that? That is an isopropyl group. I'm running out of room, so I'll write it underneath, and it's an alcohol, so the common name for that is isopropyl alcohol. And isopropyl alcohol, in fact, I've worked at companies, we just call it IPA, but isopropyl alcohol is used a lot. You take that 70% or higher, mix it with water, you get a homogeneous solution we call rubbing alcohol. And finally, the last one, we look at this, the longest chain, 3 carbons, propane. It's an alcohol, propanol. The hydroxyl group is carbon 2, and we also have a methyl group. So the IUPAC name, which nobody ever uses, 2-methyl-2-propanol, but I rotate the molecule 90 degrees to get this molecule right here. And if I go like this, whoops, what do you see? A T-butyl group. And therefore, the common name is T-butyl alcohol. On a test, I'll never ask you, here's the structure, what's its common name? But I will ask you, here's the common name, know how to draw it. Why? Because that's how you're going to see ingredients on a label. A lot of times for these type especially, you'll see the common, not the IUPAC. So ethanol, common name, ethyl alcohol. 2-propanol, common name, isopropyl alcohol. And the last one, 2-methyl-2-propanol, nobody ever used that. It's T-butyl alcohol. And that's how you do it. Any questions? If I look at the clock, it's time to take a 5-minute break. So I will see you at 1:55. I'll be back. Hopefully you will too. Time to start again. All right, let's get back to alcohols. Now, today we're going to do a lab, and normally I would have done 50 minutes like I already done. We take a break, then we have our lab. Because I'm going to lose some time on the 4th of July, actually the 5th, that Monday, I've been stealing a little. I think this might be the last time I'll be have to do that. So I'm going to go for a little while, then we'll do our lab, and then you'll get out. All right. Now, one of the things I've done this semester, and I'm going to do now, is click this. Will this be on the test? And the answer is no. The switch is off. But it's still an important aspect of alcohols I would like you to know. So let's go through this. Hydrogen bonding of alcohols. What is a hydrogen bond? In case you forgot, hydrogen bond is a weak intermolecular. Inter means between two separate different molecules. And think about it, if you were to go on a trip, on an international trip, like I used to go, I would take a plane and go outside the United States. When I worked in the chemical industry, two companies I worked for were headquartered in the Netherlands, and I went to the Netherlands and Germany and England a lot. The other company was headquartered mainly in England, and I also went to England. That company, I used to go to Manchester. In the Netherlands, I'd go to, do I have time? Oh, I do. Little Dr. White story, because I got time to tell you a little. One of the companies I worked for was Unichem Chemicals. At that time, it was part of Unilever, a tremendous company, huge, international, multinational. And I was lucky enough, the headquarters, the division I worked for, they made certain types of molecules I'll talk more about, was located in the town spelled Gouda. Anybody ever hear that cheese, Gouda? Americans pronounce it Gouda. In Dutch, a G is a hard CH sound. And because I know Hebrew and can speak it, I'm rusty though, but I can pronounce it. I was one of the few Americans who they were surprised. You say the town spelled Gouda is not pronounced Gouda, it's Gouda. And I would take a train because Gouda is a small town, but the nearby, about a 25-minute train ride, and the trains in the Netherlands are amazing. In Europe, they're amazing. Wish we had like that in the United States that well. But anyways, I would stay in The Hague, which is the international city with the international port, but that's the English way. The Dutch name for that is DEN space HAAG, Den Haag. And I would take every morning a train from Den Haag to Gouda. Then I have about a 10-minute walk through the town center of Gouda. I'd pass the town hall and the cheese warehouse in Gouda that had been renovated many times or fixed, because both of those structures were over 100 years old before Columbus set sail. Think about that. It was awesome. I walked by a canal and they had a windmill going sometimes. It was a beautiful way to start your morning and end your day when I'd walk back to the train station. If I wasn't going out to dinner with colleagues. But anyways, hydrogen bonding is weak intermolecular attraction between non-bonding electrons on nitrogen, oxygen, fluorine, and the hydrogens on those. Now, the most famous hydrogen bond is water. Because electronegativities now, this is a Greek letter delta in lowercase. Now, this is the capital delta. In chemistry or science, this means difference, and we use this for small difference or slight difference. And this tells me in water, because the polarity of the different electronegativities, oxygen, hydrogen. Again, this won't be on test. There's a slight positive charge on oxygen, slight negative charge on oxygen, slight positive charge on hydrogen. And how many of you heard opposites attract? Just look at my best friend and his wife. They've been married over 45 years, and I still amazes me. They're so opposite, but they get together. They have, obviously. Well, there's a slight attraction, not a full chemical bond, and that's what we call a hydrogen bond. Now, in alcohols, you have the same thing. So if I have another alcohol, I can have a hydrogen bond. Now, you say, so what? Well, hydrogen bonding, even though it's a weak force, it plays an amazing role. Water is a liquid at room temperature because of hydrogen bonding. You look at molecules similar molecular weight that don't hydrogen bond, they are all gases at room temperature. The hydrogen bonding allows water to be a liquid. And think about how our world would be if water was a gas now. We wouldn't exist the way we do. Think about our blood, the water we drink, our oceans would all be gas. And this means water and alcohol can hydrogen bond, which means smaller alcohols are soluble in water. And I should warn you, don't tell bartenders, you know how you can make that drink, mixed drink with water or other things with water and alcohol? That's because alcohol can hydrogen bond to water. They don't like to hear chemistry. Trust me, bartenders don't like to hear chemistry, organic chemistry. All right, now that's one thing. The other thing I like to talk about, again, switches off, but this is an important concept, the acidity of alcohols and phenols. And the question is, what does that mean? Well, first of all, let me read the slide. Alcohols are very weak acids, but their conjugate bases are strong bases. Phenol is a weak acid, but it's much stronger acid than alcohols. And this is due to resonance stabilization of the phenoxide ion. See board. Again, switches off, but I'd like to talk about this. What's an acid? An acid is something that donates a proton or dissociates by giving up a proton, H+. Now, if you have an alcohol, and this is an equilibrium reaction, and you should have learned this from general chemistry. Now, if an alcohol is an acid, the equilibrium is that way. Tiny arrow to the right, that's because alcohols don't like giving up protons. Now, this is a very weak acid. Its conjugate base, RO minus, called alkoxide, again, this won't be on, is a very strong base, much stronger than sodium hydroxide. Now, phenol can lose a proton much more than alcohols. It's a stronger acid than alcohols. Why is that so? If I can draw it. And Dr. White's going to have some fun. By the way, my last patent, I used phenoxide anions, my knowledge of it, to make new molecules. Anyways, this is more stable. Why? Because I can draw resonance forms. And Dr. White's going to have some fun. Remove the electrons. You'll form this, and I can draw two more. I won't. And the more resonance forms you can draw of something, the more stable it is. So this is much more stable, the phenoxide, than alkoxide, because I can't draw any resonance forms there. And that's why this is mildly acidic, and that's why it tingles when you put it on your lips in Carmex. Now, alcohols also can be bases, which is still off. They're very weak bases, and they can be protonated. A base is something that accepts a proton. In other words, they react with strong acids. And this is somewhat important, even though I won't ask it on a test, because it's the first step in two important reactions I will show you. And what does that mean? It means I clicked on the wrong screen. If I have an alcohol and reacted with a strong acid, H plus, remember we use H plus as a strong acid, what can happen is this. And now this has a plus charge to it. Now, why is this an important first step? Well, if you look at this molecule right here, and if I go like this, does anybody see anything interesting you might be familiar with? Let's see. Two hydrogens and oxygen. Two hydrogens and oxygen. Notice people with beards do this when they're thinking. But anyways, or like this. I don't have a long enough mustache to do the twirly thing. But anyways, H2O, water. And what that means is when you form this, it can lose water and form this molecule. This is called a carbonium ion. And it's very reactive. And it's the first step to make a couple reactions I will show you. All right. Now, how do you make an alcohol? Oh, look, you already know this reaction, but you didn't know it when it was called an alcohol. And that is, if you take any double bond, react acid and water, you will get an alcohol. I don't have on here, I should. And it follows Markovnikov's rule. Of all the general reactions I will give you, this is the only one I can put on both tests 1 and 2. And why don't you try this one for your fun and enjoyment on this Wednesday afternoon? I hope you all got out yesterday afternoon or evening, early evening, to enjoy the beautiful wind, nice temperatures, low humidity. I was on my back deck enjoying the weather and just taking it easy for a half hour before I got back to work teaching, grading things. And when you're done, I'll let you do a thumbs up today. A couple people are done. A couple more. I think everybody's done. So I better get to work. And the answer is, what do you see that's different? Double bond. Double bond reacting with acid, H plus water. Remember, water is H, OH. And here, what do? We break the pi bond. One carbon gets H, the other gets OH. Remember, double bond, one pi bond, one sigma bond. You break pi bonds like this, but sigma bonds, single bonds, you don't. And remember, this follows Markov-Nikov's rule. And that is the carbon of the double bond with the most hydrogen gets the hydrogen, and the other carbon gets the hydroxyl group, OH. So if we look at the two carbons of the double bond, how many hydrogens does this have? 2. How many this one? 0, which is greater. Hopefully all pick 2. You break carbon-carbon single bonds? No. But I do break pi bonds. So I start with 4, I end up with 4. Which carbon has the most hydrogens of the double bond? This one, that will get the hydrogen. The other one will get the hydroxyl group. And don't forget 4 bonds to carbon. Oh, let's do another one. And here's one more for you to have fun with. All right, when you're done, give me a thumbs up. Might see a couple people done. All right, I think everybody's done. Or somebody's thumbs up buttons are broken. Hopefully that's not the case. All right, let's get to work. Look at this molecule. What's different? What's not a carbon-carbon single bond or carbon-hydrogen? And look, double bond. And what am I reacting with? Acid and water. Remember, water is HOH. You break the pi bond. Remember, this has one pi bond, one sigma bond. And one carbon gets the H from water. The other carbon gets the OH from water. And how do you know? It follows Markov-Nikov's rule. The carbon with the most hydrogen on the double bond gets the hydrogen. The other gets the carbon with double bond gets the hydroxyl. Or as I learned it years ago, many years ago, the rich get richer, the poor get poorer. And we're talking about hydrogen. Oh no, it's a ring. I don't see any hydrogen. Wait, there are 4 bonds of carbon. You have to count. Here are my 2 carbons in double bond. This one right here has 1, 2, 3 bonds. 4 minus 3 is 1. It's got 1 hydrogen. This carbon down here has 1, 2, 3, 4. 4 minus 4 is 0. Do you break carbon-carbon single bonds? No. So I still have my ring. I have my isopropyl group here. I have my methyl group here. That comes along for a ride. I have my methyl group here. Now, this carbon gets the hydrogen. I'm done. This carbon gets the hydroxyl group. You put the methyl group here and hydroxyl on the other side, that's okay. It works. And with that, guess what time it is? It's lab time. And today's lab we'll be going through in a second. Don't forget the lab we did on Monday is due today. Get it in today or at least by tomorrow morning at the latest. And because otherwise you can lose 11 points. That's not good. Also, if you haven't noticed, in D2L, I have posted the scores from the first lab. One of the bad things about teaching online like this is where we don't see each other face to face, like in the lab. I can't hand you back the lab and you can see what I marked wrong. But always feel free to ask me. Remember, there's no such thing as a dumb question. You can ask me and I will tell you. I think I mentioned earlier for the test, I found a way how to get back, but it's just too much work and not too much work for labs. All right, today's lab deals with electrophilic aromatic substitution reaction, and it deals with directors. And let's take a look at that lab. Everybody see aromatic electrophilic substitution lab on the screen? I assume so. Now, this lab, if we were face to face, you'd be working with concentrated sulfuric and concentrated nitric acid. And this is one where I have students wear a long sleeve top and gloves and safety goggles. It's dangerous. Sulfuric acid and concentrated nitric acid are very hazardous chemicals. In fact, one of the worst accidents, a very bad accident I saw happen in my lab at the other school was a student didn't follow directions. And also because at that time I didn't have them wear long sleeve top or a lab coat to protect their skin on their arms. They didn't follow directions. They put a whole milliliter in the eyedropper of nitric acid on his forearm. I happened to be about less than 30, 40 seconds away, grabbed him, put his arm under cold water. Even though I did it so quickly, he still had a really bad acid burn. And all the years I've taught this lab and all the hundreds of students who've done it, that's the only time we had an accident because he didn't follow directions. And that unfortunately happened, but that happened. Well, you're not going to be using it, but I still want to talk to you. Now, what we're going to talk about is electrophilic substitution. And that's where you take a benzene ring, the CE electrophile, and it replaces one of the hydrogens with the electrophile. Now, what happens when there's something on the ring already, a substituent, which organic chemists on benzene rings call Z? How that happened, I don't know. But now, if you have Z, the incoming electrophile can go in the ortho position to Z, 1, 2. It can be in the meta position, 1, 3, or it can be in the para position. 1, 4. And Z is called the directing group. It's like those nasty people at the concerts where they take a field, make it into a parking lot and tell you where to go. They don't like me because I don't listen. But anyways, Z tells the E group where to go. And that's called the directing group. Now, when it comes to directing groups, there are two types of directing groups. First type is ortho para. And you get a mixture sometimes. Now, once in a while, if Z is very large, you'll only see para. And if you only see para in this type of reaction, it's still called an ortho-para abbreviated director. And sometimes Z can be very big and it blocks the ortho position. We call that steric hindrance. We have a lot of fancy words we use in organic chemistry. But still, even though you only get para, it's called an OP director, ortho-para. Now, the other type is a meta director. Yeah, that's the only one you would get. Now, today's lab deals with the following reaction. You're going to take bromobenzene, and if we were in the lab, you do it, and you'd react it with nitric and sulfuric acid, and this puts a nitro group on it. Now, the lab today is to determine what type of director is bromine. And you got two choices. It's either ortho-para director or meta. Now, what you do is you put a nitro group on that benzene ring. Now, I'm going to do something which is a way of saying, I'm not going to tell you the answer now. And somewhere on that ring will be a nitro group. And it's your job to find out. And what you would do in the lab is you would run the reaction, and turns out bromonitrobenzene, all the three isomers, ortho, meta, and para, are solids at room temperature. And you take the melting point. Unfortunately, at this school, we only have an hour and 50 minutes. You make it, you show it to me, and I'll tell you the melting point. At COD, we have 2 hours and 50 minutes. Students may isolate it and may take the melting point. And here, if you notice the actual reaction I have there, I'm just not giving away what isomers you're making. Now, in YouTube, you can watch on your own how to do this reaction, but I'll go through the procedure right now. In a round bottom flask or in a beaker, you'll put in some water and boiling chips. And let me teach you something about boiling in case you're not familiar. How many of you have ever boiled water in the kitchen? I think most of you have. Oh, by the way, it's permitted to laugh when I do artwork. But in a glassware, say you're going to boil water, and here's your heater. Here's your plug going to. But anyways, when you boil water, water vapor forms, it bubbles, and they come out. And when the vapor pressure, the gas from the bubbles, equals the atmospheric pressure, that temperature is the boiling point of water. And we're going to use water to heat this reaction up. But if you have in glass, unlike metal, which even though it feels smooth, it's very rough when you're talking about boiling, you have to put in boiling stones. And boiling stones or boiling chips are inert material. It can either be marble chips, they use those at COD. At ECC, we have some more money, so we use it's called carborundum chips. They're just very rough, and they help the bubbles form so you don't get big bubbles and everything splashes up, which we call bumping, and bumping is bad. You can get burned too. And that's why whenever I microwave water just to heat it up, I'll put a piece of rice, uncooked rice in there, so the water won't bump. If you ever heard of people taking boiling water out of a microwave and all of a sudden a lot of it bumps up, it's bad. It's dangerous. So you'll get your beaker and you'll start it because it takes a while to heat it up. After that, in a small 25 milliliter round bottom, you'll carefully add 3 milliliters of sulfuric acid using a glass funnel. Now, that's where the student made the mistake in the next step. Let's see if I can. All right, everybody see on their screen this round bottom flask? You see that now? Thumbs up, people, help out. Hold on. Yep, you see it. And this one's a 2440. We use a smaller one. And you would put a funnel in here. And this is the type of flask you would do the reaction. And we use these a lot. In fact, I have a collection of these in my house that I bought on eBay because I'm a chemist and I like things like that. Now, after putting the sulfuric acid in, you put it in an ice bath, ice and water, in a recrystallization dish to get it cold. Then you slowly add the 3 milliliters of nitric acid in 3 parts with an eyedropper and a glass funnel. That's where that student at one time, and I missed it. And after that, I've always keep on, when you're doing this, say use a glass funnel every 2 minutes or more. Didn't, and he had trouble getting the eyedropper in the small opening of the round bottom. But you do it, you swirl it, then you take 1.6 milliliters of bromobenzene, put it in there, swirl it for 1 minute, let it come up to temperature for a while, then you put it in the boiling water for 25 minutes. Now, I haven't talked about it much, but there's something called side reactions. And when you run chemical reactions, sometimes impurities react with other things to make things you don't want. This one happens. The first time I ran it, what the heck is going on? But you do this in a hood, which protects you. A hood is a fume hood, which takes fumes away from you and directs it to the roof where it can be diluted by the air above the roof of a building. And this one, if you look at the YouTube, I forgot, you'll see brown smoke. And that's missing the word smoke. I don't know why. Coming out. Now that's nitrogen dioxide, which is a poison, but you're in a hood, and that happens 9 out of 10 times you'll see it. And you'll let it cool, and then you'll see a solid. Now, since we don't have the time to do a melting point, isolate it and do a melting point, I tell you the melting point. Now, a couple things I want to show here is, if you notice at the very beginning, we put in sulfuric acid and then nitric acid. Why do we do that? And the reason why is nitric acid, what you're doing is HNO3 and H2SO4. And think of HNO3, nitric acid, I can write it this way. And think of sulfuric acid as an acid, which I'm just adding H+. And the hydrogen ion goes there. And forms this. If you notice right here in the molecule, 2 hydrogens and an oxygen. Oh, that's water. Whenever you form water, it likes to leave. And minus H2O means it leaves. What you're left with is this, the nitronium ion. Remember, anything we do in lab will never be on test from the lecture. And this is the electrophile, which attacks the benzene ring. So this is the important species when you react nitric acid and sulfuric acid. What you're really making is that. And that attacks the benzene ring and bonds to it and puts on the nitro group. Now, in the real world, if we were doing this in a lab, I would ask students, when you get the solid, call me over and I'll write my initials. Did I tell you about my initials? Freshman year, high school, non-Western civilization history class, I was bored out of my mind. I listened, paid attention, but I was still bored out of my mind. I got the highest grade A in that class, but I was still bored. And so I said, well, what can I do to not be bored? I said, I needed a monogram. So I came up with this. This is a W with a K inside. And I've been doing that ever since. I think it's cool. Anyways, that tells me you got the solid. If not, I'd take off points. Then I would tell the student the melting point, if you did it in the lab, would be this way. And here are the melting points of the 3 isomers of bromonitrobenzene. And right here, you have to identify which isomer or isomers did you get. And generally, you're going to have a melting point a little below this is called the literature values. Which someone, more than one chemist has made this, taken the melting points and recorded it, published it in scientific papers. That's why we call it. And here we have questions you have to answer to hand in with the lab. So what you have to do for this lab is identify which isomer and then answer these questions. And with that, I'm done. Let me remind you, if you need any help, come to my office hours. There's one tonight from 6 to 7:15, and stop by. What I was thinking, don't forget, it's a different Zoom login than the lecture. And with that, I'm done for today. If we had been in the lab, right now you go in the lab and do what you saw, and you get out about 10 to 4. But you're not going to do that because you're at home and you're not going to use those chemicals ever. I wouldn't either. With that, I'm going to say, Gang gesund, goodbye.